Now we will solve the last geometry because we have already solved the line geometry in the cylindrical case, the spherical geometry. We have found the electric field inside a spherical shell, inside and outside of it, then inside and outside of a solid sphere. Similarly, we have found the electric field inside a solid cylinder. So, keeping this thing continued, we are now towards the final geometry, and the geometry is of a sheet. We are having a sheet of charges, and we will calculate the electric field due to that sheet of charges. So let me recite example 2.4, and it is visible to you on the screen as well. So the example says, an infinite plane carries a uniform surface charge sigma. Find its electric field. So the value of the surface charge is given on a sheet, and we are supposed to find out the electric field due to this sheet of charges. So here let me first draw the sheet here. Let's say this is an infinite sheet of charges. So the ends will be somehow like this, and on this side as well. This is just for showing that the ends are infinite along each side, and the surface charge on this one is sigma, such that sigma is equal to the charge per unit area. Now, what is the electric field here? We will have to find this one with the help of Gauss's law. From Gauss's law, we know that E dot dA is equal to the enclosed charge divided by epsilon naught. So this is a closed surface integral, and this is the Gauss's law. Now we will apply this one, but as we consider a concentric sphere in the case of a sphere, and a coaxial cylinder in the case of cylindrical geometry or line geometry, now we will consider a shape on the sheet, and that shape we call is the pillbox. So we will consider a box on this one. The box is such that it is just like here, means this box is halfway up and halfway down this sheet. And let me show it with a different color here. So this box is halfway up and halfway down on this sheet. So this is kind of a pillbox, and it is basically cutting the sheet at the half point, like it is above and below this one. So this electric field on this one, it is here. This is the electric field here, and the sheet, this one, the portion, this is the portion which is just above this one, and it is here of the sheet, and then this one is just below this one, it's here. Like this is the portion of this box which is just below this sheet, and the electric field is in this direction. Now it's just like a page, and sheet, it's a page, and there is a box which is halfway up this one and halfway down, and we are having the area of this is A. So below face is also having area A, and the above is also having area A. It's the same box here. Now we will count the two areas here. If I look here, then the electric field lines are in this direction, and this area is also in this direction, which we call the perpendicular area, which we represent is the n. So it is area along the unit vector n, we call the normal vector, and similarly downward here as well. But keep in mind one thing, here we will count the upper pace and the lower pace, while these sides are not contributing to the electric field, because the area here is in this direction while the electric field is in this direction, and that's why these surfaces will not contribute, and the flux due to these surfaces, this one and this one, they will be equal to 0, and we will only have the contribution from here. Now, why we are considering the up and down surfaces? Why not only up? So understand this situation, that why we will have to do this. For example, you take this page, and on this page you put some water. Now the thickness of the page is negligible, and the water will appear on both the sides of this paper. So water is one entry here on this one, while it appears to be above as well as below. So we are counting two areas here, but the source is actually one, and that's the reason that the result will come out to be half of that thing. So it will be then on the closed surface, the curve, these surfaces will not contribute, and only the upper and lower surfaces will contribute. So this will be equal to E and dA, they are in the same direction, and cos of this will be equal to 0. So this is equal to the surface, so I will write EdA, and here the charge enclosed is equal to sigma over area here and epsilon naught here. Now this is E, we are not integrating on this one, and we will have the area here. So let's say this is the upper, you write here like this is the upper area, and then we have the electric field here, and this is the downward, this area here, and dA, and this is equal to EA, because area of this side is A, and plus the area of the other face, this is also A, and this is equal to sigma over, this is Q enclosed. So Q enclosed, okay, let me make one correction here. This is Q enclosed, so Q sigma is basically Q enclosed over area. So Q enclosed will be equal to sigma A, and this is not here. This is sigma times A here. So we will have this is sigma A and divided by epsilon naught. And now this we will write is E times 2A, like 2EA equals sigma A over epsilon naught, and AA will cancel with each other here, and we will have the electric field equals to sigma over 2 epsilon naught here. And if we write this thing in vectorial form, then this will be the vector form, and here we will have this is normal to the surface. The electric field is normal to the surface along their direction, and we are having the electric field of an infinite sheet of charges like this. We can discuss the solution here. Is here we know that electric field of a sphere, electric field of a line charge, electric field of a cylinder, they are all dependent on the distance from the sheet, dependent on the distance from the source. But if I look here, the electric field is completely constant. This is sigma over 2 epsilon naught. Sigma is constant, 2 epsilon naught is constant, so electric field is constant. The reason for this is that we have considered an infinite sheet of charge. This is not finite. If this would be finite, we would have a decreasing field. As this is infinite, so that's why we will have a constant field and it will not be decreasing. This is for example, if the observation point is here, then these are the charges which are in interaction here. And as I remove this one here, then the distance is increasing and the area is increasing. The interaction area, or the number of charges coming in this field of view or this interaction, is increasing. And as I go away from this one, more and more charges are coming into action, which keeps the electric field to be the same and not decrease at all. So that's the reason that we are having a constant electric field. While in example 2.5, we are almost having the same geometry, but with two sheets of charges, and now they are two parallel sheets of charges here in example 2.5. So we will actually incorporate the same result here as well. Okay, let me recite the example which you are seeing on the screen as well. Two infinite parallel planes carry equal but opposite uniform charge densities plus minus sigma. Find the field in each of the three regions: to the left of both, between them, to the right of both. So we will have to find the electric field in three different regions, and the regions are such that, let's say we are having sheets of charges and they are like this. We are having, this is one sheet of charge. Okay, keep in mind one thing, that they are infinite. They are infinite along each dimension. I am trying to show them along one, and then here as well, this will be like this. Here, this is also infinite, and the sheets are like this. Okay, these are two sheets of charges, and on this one we are having sigma plus, while on this one we are having sigma minus. Sigma plus means that we are having positive charge on this sheet divided by the area of the sheet. Both are having the same area as both are an infinite sheet of charges. While sigma minus means that this is Q minus divided by A. Negative charge is there on this plate. So we are having negative charges here and positive charges here. Now it is saying to find the field in these three regions. The regions are, this is region 1, this is region 2 and this is region 3. Find the fields here in these three regions. Now the geometry is such that, let me consider this one. The field of this one, this is out of this sheet, is it was just perpendicular to this sheet. So if this sheet is like this, then its field is in this direction for positive charges. So the positive field here is in this direction. This is the electric field of the positive plate of the positive sheet of charges, and this electric field, even here, it will be in this direction from this side, and this is again E plus here. And if I look on this side, then the electric field is in this direction, just perpendicular to this one. This is E positive. And I can write the vector symbols on these. And now consider the electric field due to this sheet, the negative sheet of charges. So the electric field of this is directed here in this direction. This is the electric field because it will be converging electric field, and it is in this direction. And at this point, it will be again converging here, and this is E minus. Similarly, the field here at this point for that sheet is also in this converging direction, and it is the electric field here. Now look at the situation. As we know that the charges are the same, or the sigma is the same, means they are just positive and negative, their magnitude is the same. So what about here, these two fields? This field is in this direction and this field in this direction. So the net field here in this region is equal to 0. While if I look here, the electric field is in this direction, while here the electric field in this direction. So we are having the electric field 0 here as well. The net electric field is 0 in region 1 and 3. While if I look here, then in this region, the electric field is in the same direction. It means that the electric field of positive minus the electric field of negative is opposite to it. So this is minus E here. And okay, this one, right, this one is negative, not positive. So this is negative. And here we have the electric field. This E is minus, so we are having this equal to E plus E, and this is equal to 2E. The field is 2 times the field of one sheet. So the fields are like this. Now we can write here that in region 1 the field is 0, in region 3 the field is 0, while in between the two sheets we are having the electric field equal to 2 times E. This net field, this is the, I will say the net field is equal to 2 times E. Now E is the field of one sheet, and that is equal to sigma over 2 epsilon naught. So this is sigma over 2 epsilon naught, and in unit vector, and 2 will cancel with each other, and we have the net field equal to sigma over epsilon naught in n unit vector direction. This means that this was the field of one sheet, so it was half of this sigma over epsilon naught, and for the two sheets this is equal to sigma over epsilon naught. Now, if for example, in problems the geometry is changed, like we are having both as negative sheets of charges or both as positive sheets of charges, then what will be the situation? The situation will be that the electric field of this in this direction and this in this direction, and this field will be in this direction. So here we will have the net field equal to 0, while here the fields will add up. We will have a double field here, and similarly on this side. So in region 1 and region 3 we will have a non-zero field, and in region 2 we will have zero field. This is the same situation when we are having two equal and opposite charges. So the situation is that in between them, at the center here, we are having a zero electric field, while the electric field is here, is non-zero in other directions. But at that point, we are having the electric field equal to 0. So this way, we have solved some geometries, and the geometries are now complete. We solved the line geometry, the sheet geometry or the area geometry, and then the volume geometries we solved for two familiar surfaces. We solved it for a spherical geometry and for a cylindrical geometry. So with this, we are done with the applications of Gauss's law, and now we will consider is all these were based on the divergence of electric field. So now we will start with the curl of electric field.